The final thing we're going to talk about here for rotation is situations that involve combinations of both linear momentum and angular momentum. Before we do that, though, we need to talk about a way of going in between those two quantities. And so for a second, I want you to consider an object with some mass moving to the right at some velocity. We would say that object has linear momentum, of course. It has a mass, it has some velocity. We probably wouldn't say that it has angular momentum because it's not rotating. However, we can consider the angular momentum of this object, all right? And the only thing we need to do in order to consider it is we need to create a pivot point. So as soon as we create a pivot point there for our object, okay, we can now consider the angular momentum of this object about that pivot point. Now, in a lot of situations, it's not useful. However, if we have some situation that involves angular momentum in addition to linear momentum, now it becomes a useful quantity, becomes a useful thing to consider. So when we do that, when we pick our pivot point and consider the angular momentum of a linear object about that pivot point, okay, we get this equation here. L equals RP sine theta, which looks very similar to the way that we solve for torque from a force. It's actually identical, except instead of angular momentum and momentum, it was torque and force, okay? And so what this equation is we think about the linear momentum, mass times velocity of the object. We think about r, the distance from the pivot, okay? And theta, the angle between that r and the direction of our momentum, which would also be the direction of our velocity. In case you're curious, there is one other way of thinking about the angular momentum of a linearly moving object, and that is we could, let's say this is our pivot and there's the velocity of our object, we could think about the object as a point mass, okay, and actually calculate its angular momentum about that pivot point some distance r away. And so in that case, we would say our angular momentum is just I omega, right? That's our old definition for it. If we have a point mass, okay, the moment of inertia of that point mass is mr squared, all right? And then the angular speed, all right, is just going to be our tangential velocity divided by our radius r. The r's cancel out there, and if we do a little rearranging, we get that L is just r times mv. This mv here is the momentum, okay? And so we're left with the same equation that we have here. The only difference is that sine of theta term, and that just corrects for a situation like this where we're not necessarily moving perpendicular to the radius. We're not, it's not truly a tangential velocity. But when we're here and at a 90-degree angle, that sine of theta term just goes away. So this is another way of thinking about finding the angular momentum from the linear momentum. Let's go ahead and try a practice problem with this. So we have a ball thrown at a hanging wooden rod that pivots about its top. There's the moment of inertia of the rod. Has a mass that's 3 times the mass of the ball and a length of L. Initially the ball is moving at a speed of v. Afterwards it rebounds with half as much speed. So we want to derive an expression for the angular speed of the rod immediately after the collision. So we're going to think about conservation of angular momentum here. We can't think about linear momentum in this case because we do have a force from that pivot point, from that hinge. That would be an outside force on our system causing linear momentum not to be conserved. However, our angular momentum is conserved because we have no outside torques. If we pick this as our pivot point, that force from the hinge does not create a torque, and therefore angular momentum is conserved. So initially we have the angular momentum of the ball. Afterwards we have the angular momentum of the ball, its final, plus the angular momentum of the rod, okay, because both are going to have angular momentum, both are going to be moving / rotating afterwards. So we're going to bring in our equation that we just learned for the ball. So we're going to say its initial angular momentum is rp sine of theta. Its final is going to be r times its final momentum times sine of theta plus the angular momentum of the rod, which is going to be I omega. So for the ball, we're going to think about its radius. It's going to hit right here. So the distance away it's going to be is just going to be L the length of the rod. Its momentum is going to be its mass, which I'm just going to call m. All right, we do know the rod has a mass that's 3 times as much, but I'll just say the ball has a mass of m, and its velocity is v here. The last thing to think about is our angle, and here's what I'm going to do. I'm going to consider the point right before we have that collision. And at that point, the object's traveling directly to the right. My r is just from here to here, going straight down, and so the angle ends up being 90 degrees, so just times sine of 90. I should point out it actually doesn't matter what you end up doing there. Let's say we did want to think about the object when it's a little bit further back from our pivot here, let's say at this point here, and we'd have some new distance between the pivot and our object. That would be r. The angle would be theta here, and we would ultimately end up having our momentum times r sine of theta. However, if we think about this, r sine of theta happens to be, okay, that side of the triangle here. Okay, this is a right triangle. It happens to be that side, and it's going to be equal to L, right? No matter how far away we are, whether we're here or here, if we take the distance from the pivot to where we are times sine of the angle between our r and our momentum, it's ultimately going to be this side of the triangle, which is always going to amount to L. So I picked the point right before, where that sine of 90 term just goes away, and we ultimately just multiply our momentum times L, the length of the rod. But it actually doesn't matter where you pick, it's all going to work out mathematically to be L. So that's going to be equal to R afterwards, which I'm going to keep as L. The momentum is going to be m and then negative v over 2 because we're rebounding. All right, still sine of 90. Plus our angular momentum term, so plus our moment of inertia, which is going to be 1/3 times our mass. For the rod, it's 3m, because it says it has 3 times the mass of the ball, times L squared times our angular speed, omega. We can simplify this here, and it becomes LmV equals negative 1/2 LmV plus 1/3 times m just gives us mL squared omega. We can do two things. We can cancel out the m's. We can cancel out the l's. They're also in every single term, or at least one of the l's. All right, and then we can go ahead and solve for our angular speed. So what I end up getting when I add this term over is 3/2 v equals L omega, and so it just ends up being 3v over 2L equals our angular speed. So for this one, what I'm going to be thinking about is the fact that the change in angular momentum is going to be equal to the area on that graph. So the first thing I'm going to do is solve for my change in angular momentum, which is just going to be my final angular momentum minus my initial. My initial for the rod was just 0, so that goes away. So my change in angular momentum is going to be the moment of inertia of the rod, 1/3 times 3m times L squared, okay, times my angular speed, which is 3v over 2L. When I go ahead and simplify this, canceling out some of the things I can get rid of, I end up with a final angular momentum for the rod of 3mLv over 2. Okay, and that's going to be equal to the area on this graph, all right, the area of this triangle here. And so that's going to be 1/2 base times height. So we can say our change in angular momentum is 1/2 t times that torque, which is just tau. We set those equal to each other, so 3mLv over 2 equals 1/2 t times tau. Those 2's cancel out, and we're left with a maximum torque here of 3mLv over t. Okay, and so there's our answer to that part. The last question asks, how would my answer to A change if the ball is replaced with a piece of clay of equal mass that's stuck to the rod after the collision? And what would end up happening is that angular speed would decrease. And the reason for that is that the clay would experience a smaller change in momentum because it wouldn't rebound off of the object. And so that means that the rod then would have a smaller change in momentum as well. Okay, we know that in any system where momentum is conserved, the change in momentum of each object is equal, and so if the clay experienced a smaller change in momentum, the rod would also experience a smaller change, and overall, it would be traveling slower than it was if the ball bounced off like it did.